We are in chapter 6 now. Specifically, we need to see sections 6.1 and 6.3. 6.3 is actually what is interesting for us. Section 6.1 gives a general idea and some reminders of the dot product, and it generalizes it, and now it's called inner product because we can have it also for functions, polynomials, and also different inner products for vectors. Now we are not interested in checking all that, so for us section 6.1 is a little bit of a reminder and something that we are not really interested in. We will focus on section 6.3, and I will make some recalls, reminders of what we need actually, just to refresh our memory. So chapter 6, and specifically section 6.3, will deal with orthonormal basis or orthogonal basis. So how do we get these bases? For that we will need to use something called Gram-Schmidt orthogonalization process. So the idea will be that we start with one basis of a linear space, and then we apply Gram-Schmidt orthogonalization, and we will get, after that process, an orthogonal basis. And then we can transform that orthogonal basis into orthonormal basis. So we will see the examples for all that. This part is actually quite simple. So before we go to Gram-Schmidt, I'll just make a couple of reminders about norm and unit vectors, because these are things that will come and will be useful. So if I have a vector with n components here, the norm is the square root of the dot product. Also in 6.1 they introduced the name inner product, and they have this exotic notation. For us, we are going to deal with vectors only, and we will deal only with standard Euclidean dot product. So we are interested only in dot product. So norm for us will be radical of the dot product, something from high school. So obviously norm square is the dot product. Reminder here of the result: if you multiply a vector by a number, by a scalar, then the norm of that new vector is absolute value of the number times the norm of the vector. When the norm is 1, then the vector is called unit vector. So we know that. How do we get vectors with norm 1? Well, it's not complicated. We take any vector, v, we compute the length or the norm of the vector, so radical of the dot product, and then we divide vector by that number. So we divide every single component of the vector with the norm. So what we get is a vector u, and this vector is unit vector. The norm of u is 1. So this process is called normalizing vector v. So once you normalize a vector, you get another vector u that is of norm 1. So this will be useful when we want to get orthonormal basis. So just normalizing a vector. Reminder of orthogonality of vectors. For us, again, it will be just simple dot product. So two vectors u and v are orthogonal when their dot product is 0. So this exotic notation also works, it's fine. It's called inner product or dot product for us. So two vectors are orthogonal when their dot product is 0. Obviously, if dot product of two vectors is 0, any scalar multiple of vectors, well, their dot product will also be 0. So a times u dot b v, well, obviously the dot product will be 0 because u and v are orthogonal already. So any scalar multiple of orthogonal vectors will still be orthogonal vectors. So that's something that will be useful in this Gram-Schmidt process eventually. So here are some examples. So I have vector u and vector 0. Obviously, vector 0 is orthogonal to every single vector in the linear space, because the dot product is 0 always. Dot product of these two vectors, if we compute, it will be 0, so they are orthogonal. These two equally, they are orthogonal. And then here we have three vectors, v1, v2, v3, and if you take any two of these vectors and you do the dot product, you'll get 0. So the vectors v1, v2, v3 are also orthogonal vectors. Obviously, any scalar multiple of orthogonal vectors will give you orthogonal vectors. So 5 times v1 dot product 6 times v2 will be 0 also, because v1 dot product v2 is 0. So you can just quickly compute dot products and see that they are 0. And this is again a property that can be useful later on. Any scalar multiple of orthogonal vectors is still orthogonal. So if I take my orthogonal vectors and I put them in a set, then that set is just called orthogonal set. All that means is the vectors that are in that set, their dot product is 0. You take any two vectors from the set, the dot product will be 0. So that set is called orthogonal. Just because the people who are living inside, their dot product is 0, they are orthogonal to each other. Now the good news with orthogonal vectors is that if you have a set of orthogonal vectors, non-zero vectors, then they are automatically linearly independent. So that's great. So if you have an orthogonal set of non-zero vectors, they are automatically linearly independent and form a basis of span of S here. It's very simple. Orthogonal vectors, different from 0, they are linearly independent. Obviously 0 is orthogonal to every other vector, but we know also that 0 is linearly dependent, and also 0 will make any set also linearly dependent. Okay, so that's why we exclude 0 from the gang. So we say orthogonal set of non-zero vectors, they are automatically linearly independent. So 0 is not a candidate anyways. So if I have such set of vectors, then I have a basis. Orthogonal non-zero vectors, they form a basis. So that basis is called orthogonal basis because of the property of orthogonality of the vectors. So orthogonal basis is just a basis formed by orthogonal vectors. That's it. This is just vocabulary and definitions. What is important is this property here. Set of orthogonal non-zero vectors is linearly independent. That's important. Now I can normalize set of non-zero orthogonal vectors. Then I will get vectors with norm 1. So if I have a set that is orthonormal, what does it mean orthonormal now? Well, that's a set that is actually orthogonal, so everybody is orthogonal in the set. So 2 by 2 they are orthogonal, the dot product is 0. But also the norm of each vector is 1. So each vector is actually a unit vector. So orthonormal set is set of orthogonal vectors and each vector has a norm 1. So obviously an orthonormal set is automatically linearly independent. Why? Well, because that's an orthogonal set of non-zero vectors. And that one is linearly independent, obviously. The fact that we require here that the norm of each vector in the set is 1, obviously that eliminates vector 0, because norm of 0 is 0, right? So we know automatically that orthonormal set is also linearly independent. So we can have orthonormal basis for a linear space. What is orthonormal basis? Well, that's a basis of a linear space, but every vector inside is of norm 1 and vectors are mutually orthogonal. So that's what it means. One example of orthonormal basis is your standard basis of Rn. Why is this important? Well, when we are looking for coordinates of a vector in a basis, usually we need to solve a linear system Ax equal b, and that requires some work. Well, if we are dealing with orthogonal basis, in order to find the coordinates of a vector in an orthogonal basis, it's very simple. It's just ratio of dot products actually. So I have vector y that belongs to subspace W, and this is an orthogonal basis for W. So obviously y is a linear combination of basis vectors. Now what we want is C1, C2, C3, Cp. So these coefficients, those are the coordinates of vector y in this orthogonal basis U1, U2, U3, Up. Well, it's very easy to compute them because those coefficients C1, C2, C3, they are just ratio of dot products. So particularly C1 is y dot product U1 divided by U1 dot product U1. So it's a ratio of two dot products. And each time you have y, your original vector, and you do the dot product with one basis vector at a time, and you divide by the dot product of the basis vector by itself. So pretty much the norm square. So second component or second coefficient is dot product of y with second basis vector divided by dot product of y2, y2. The third component or third coordinate is simply dot product of y with third basis vector divided by dot product of u3, u3. So this is very simple actually to find and to compute. So that's why we like orthogonal bases. An orthogonal basis helps you find coefficients very quickly, just ratio of dot products. And we will see some examples for that. It's not complicated. So in a general writing, you can say, okay, if I have an orthogonal basis for a linear space and I have a vector u in a linear space, well, vector u is obviously a linear combination of basis vectors, and the coefficients are just ratios of dot products. So here we are. That's how we get it, by the fact that v1, v2, vn are orthogonal. All we do is just do the dot product, u dot product, let's say v1, and then what happens is when you compute all that, you'll get dot product v2, v1 is 0 because they are orthogonal, v3, v1 is 0 because they are orthogonal. So all of the guys are 0 after. So all you have is dot product of u and v1 equal to c1, v1, v1. So that's how we get it. So that's really simple. So that's why we have the ratio of dot products. Straightforward. So if we have an orthogonal basis, we could solve Ax equal b, but that's not necessary. So there's no need to solve Ax equal b. All you do is just do the ratio of dot products, and those are your coordinates. So we will see an example. The computation is very simple. Here, let's say we are given vectors v1, v2, v3 in R3. They are here. And we need to verify that these guys form an orthonormal basis for R3. Okay, we have three vectors in R3. That's good. So how do we verify this? Well, we need to see if they are forming orthonormal basis. So what is orthonormal basis? Well, it's an orthogonal basis where each vector is of norm 1. Okay. But what is orthogonal basis? That's a basis where each two vectors are orthogonal to each other. So what I need to check first is if I do the dot product of each two vectors, I should get 0 because they're supposed to be orthogonal. Second step is to check if the norm of these vectors is 1. So let's see what's going on. I do the dot product, so dot product v1, v2, I compute, I get 0. v1, v3, I get 0. v2, v3, compute, I get 0. So v1, v2, v3, they are orthogonal to each other. So they form an orthogonal set. So that's good, they are orthogonal. Now let's see, so since they are orthogonal and they are non-zero, I know that they are linearly independent by the theorem seen previously. So I already know they form a basis for R3. So let's see now what is the norm. So I do the dot product, norm is square root of dot product. So v1 dot product v1, it's 1, so root of 1 is 1. v2 dot product v2, compute, it's 1. And v3 dot product v3 is 1 again. So v1, v2, v3 are unit vectors. So that's great. So they are orthogonal to each other and their norm is 1. Therefore, the set of v1, v2, v3 is an orthonormal set. And we already know that an orthonormal set is linearly independent automatically. So I have 3 linearly independent vectors from R3, they form a basis of R3. So that's very straightforward. So v1, v2, v3 form an orthonormal basis for R3. So that means every vector in R3 is a linear combination of v1, v2, v3. Okay, they are ugly a little bit, but still. So let's say I want to find coordinates of vector 1, 2, 4 relative to the basis B, which is my orthonormal basis for R3. So I know immediately that U is a linear combination of v1, v2, v3, obviously. And I know also what are the coefficients. So what are the coordinates? It's just ratio of dot products. So it's U dot product v1 divided by v1 dot product v1. So that will be the first coordinate. Second coordinate is here, and third coordinate. So let's compute them. Well, since these vectors v1, v2, v3 are unit vectors, then these dot products in the denominator are all equal to 1, obviously. So let's compute the dot products in the numerator. So U dot product v1. We compute, we get this number here. U dot product v2, we get this number. And U dot product v3, after computation, we get this. So v1, v2, v3 are given here for your reference, and U is here. So you just do the dot product. Okay, so the coordinates of vector U in basis B, which was orthonormal, are just these numbers here that we got from scalar products. Very simple. So now the big question is, how do I get an orthonormal or orthogonal basis? Well, that's why we need the Gram-Schmidt orthogonalization process. So we take a basis for a linear space and we applied this Gram-Schmidt orthogonalization process. We will see what it is. It's not complicated at all. It's very simple. And at the end, what I get is a set of vectors that are orthogonal. So I get my orthogonal basis for the linear space W. So I start with some basis B, I apply Gram-Schmidt, and at the end I get an orthogonal basis. After that, I could decide to normalize those vectors, and then I will have orthonormal basis. So that's the main idea. Take any basis and create an orthogonal basis using Gram-Schmidt. And how the process works is going to orthogonalize one vector at a time. And each newly orthogonalized vector is orthogonal to all the previous vectors. So that's beautiful. And again, orthogonal means just that the dot product is 0. So our goal is very simple. Learn the Gram-Schmidt process. So that's an algorithm. Very simple. And second thing is find the coordinates of a vector in an orthogonal basis. We already saw how that works. It's very simple also. So this part is really straightforward. Here is the Gram-Schmidt process. So I have a basis, some basis of a linear space, U1, U2, U3, UR. And I want to transform that into an orthogonal basis with vectors v1, v2, vr. So vectors v1, v2, vr will be orthogonal to each other. Okay? So this is the idea. This is ordered basis, so I start with the first vector. So v1 will be u1. And then v2 is u2, so the second vector, minus this part here. This is a projection of vector u2 on vector v1, pretty much. So that's the easy part. I need to remember this formula. And then what I will get is that the vector v1 and v2, they are orthogonal to each other. Next step, get v3. How do I get v3? Well, I take u3 minus the projection of u3 on v1 minus projection of u3 on v2. And then vectors v1, v2, v3 will be orthogonal. Their dot product will be 0. v4 is u4 minus projection of u4 on v1 minus projection of u4 on v2 minus projection of u4 on v3. And we continue like that. So at the end, we will get an orthogonal basis. So v1, v2, v3, v4, vr will be all orthogonal to each other. So that will be our orthogonal basis. Now, optionally, we could normalize all those vectors and get an orthonormal basis. If it's asked in the question, we need to do it. If it's not, well, we avoid doing it because it's just extra computation. So orthonormal basis is just an orthogonal basis where everybody has a norm 1. How do I get the vectors with norm 1? Well, I normalize them. I just divide every vector by its norm. So that's very simple. So what we learned is that through this Gram-Schmidt process, every vector is orthogonal to all the previously created vectors. So v2 is orthogonal on the entire linear space generated by v1. v3 will be orthogonal on to v1 and v2, so to the span of v1 and v2. v4 is also orthogonal to the span of v1, v2, v3. So this just means that every new vector that we create through the process is orthogonal to every other vector already created. That's just an observation. That's what comes with the process. We don't need to do anything. We just do the process, and this is like the benefit of the process. And again, if we need to normalize to get orthonormal basis, well, all we do is take those orthogonal vectors and divide each by its norm. So norm again is radical of the dot product. So this is an extra step, and we do it only when we are asked to do it. If the question is just find orthogonal basis, well, we don't do this step. We just do the Gram-Schmidt. But if the question is find orthonormal basis, well, we do Gram-Schmidt, and then at the end, we normalize each vector in the basis, and then we get orthonormal basis. So these are some problems that you can solve to practice. And now we are going to see some examples of the process just applying the Gram-Schmidt process. Let's see an example. So this is a reminder of Gram-Schmidt process in itself. So we have a basis u1, u2, u3, u4. How do we get an orthogonal basis using Gram-Schmidt? Well, vectors v1, v2, v3, v4 will be orthogonal if we use procedure. So v1 is u1, and then v2 is u2 minus u2 dot v1 divided by v1 dot v1 times, so this is a number, one number up, one number down, times a vector. And then v3, so it's u3 minus projection of u3 on v1 minus projection of u3 on v2. So these things are just repetition of the Gram-Schmidt process. So the process guarantees that vectors v1, v2, v3, v4 will be orthogonal. So let's say we have a basis for R3, basis B, formed with vectors u1, u2, u3. You can verify this, that these three vectors are linearly independent if you wish. So you have two choices. You can compute the determinant or produce echelon form and C. So vectors u1, u2, u3 are independent and they are basis of R3. So let's apply Gram-Schmidt process to get an orthogonal basis C from this basis B. So we start with B, apply Gram-Schmidt, and then we get basis C, that is orthogonal basis. So the process says V1 will be U1, so just copy. V2 will be U2 minus the projection of U2 on V1. So U2, copy, minus dot product U2 V1. So U2 is here, V1 is here, so it's basically this guy. So you do the dot product, you get 12 upstairs and 8 downstairs. So times V1, copy, and then you do the algebra, and this is our V2. Okay, so now V3. V3 is U3 minus projection of U3 on V1 minus projection of U3 on V2. So V2 is just the guy we computed. Okay, so we copy U3. U3 is here, we copy it. Oops, negative. And then we compute the dot product here. So U3 dot product V1. So when we do that, we get minus 8 upstairs. And we already know that V1 is 8. So these will simplify eventually. Times U1 copy. Minus. Now the dot product upstairs. U3 times V2. So dot product. So you will get 6 plus 2 minus 2, so that's 6, that's upstairs. And downstairs is V2 dot product V2, so we have 9, 10, 11. So that's what you have, times V2. So now you regroup everything, shake it a little bit, and then you get this vector here. Okay, so this vector is vector V3. So now we are done. We have started with basis B, having vectors U1, U2, U3. And then we have created a basis C with vectors V1, V2, V3. And these vectors, by construction, by Gram-Schmidt process, they are orthogonal and they are non-zero, so they are linearly independent, and therefore they are basis for R3. So we have 3 linearly independent vectors from R3, they form a basis for R3. So that was straightforward. Now we could build also orthonormal basis, starting with this basis if it's asked. So this is just computation. So let's start with our orthogonal basis C that we just computed, and let's get orthonormal basis D. What is orthonormal basis? It's an orthogonal basis where every vector in the basis is actually a unit vector. So how do we get the unit vectors? Well, it's simple. We take a vector and normalize it, which means divide the vector by its norm. So normal V1, we just compute its radical of the dot product V1. So radical 8, normal V2, normal V3. We just do the computation. So now we normalize to get vectors W1, W2, W3. So W1 is 1 over the norm of V1 times V1. So this vector is now with norm of 1. Here it is. So the norm of W1 is 1. Then W2 is 1 over norm V2 times V2. So the number times V2. When we do the work, we get this vector. So norm of W2 is 1 also. W3 is 1 over norm of V3 times V3, and norm of this vector is also 1. So now the basis D formed by vectors W1, W2, W3 is an orthonormal basis for R3. Why orthonormal? Well, it is orthogonal, obviously, because the dot product between any two vectors from here is 0, but also the vectors are unit vectors. Their norm is 1. So that's orthonormal basis for R3. You see it's a little bit messy because of the radicals. So now we can ask ourselves, having all these bases, what are the coordinates of a given vector in these different bases, just for fun. So here we have a vector z given by -1, 0, -2, so that's a vector in R3, and our goal is to find the coordinates of z in bases B, C, and D, just to see what happens. So usual procedure to find the coordinates of a vector in a basis B is to solve a linear system. So this basis is, these vectors are U1, U2, U3. So those are vectors from basis B. They are not special, they are not orthogonal really, so they are nothing special. So what we need to do is solve the system Ax equal B using Gauss-Jordan. So once you solve it, you get a solution, obviously unique. We know that coordinates are unique in each basis, 2, -1, 1. So the coordinates of our vector z in basis B that we just obtained by solving the system X equal B is here. So the coordinates are 2, -1, and 1. So to get these coordinates in basis B, we had to solve the linear system. Now the beauty of orthogonal basis is that we don't need to do this. We could. It's not a problem, but it's not smart. We already know that to get coordinates of a vector in an orthogonal basis, all you need to do is compute these ratios of dot products. So I have my basis C that is orthogonal, obtained from basis B using Gram-Schmidt. So the coordinates of vector z in basis C will be simply the ratios of dot product of z and the basis vectors divided by the dot product of basis vectors. So first component will be z dot product v1 divided by v1 dot product v1. So that's the first component or the first coordinate of z in basis C. Second coordinate will be z dot product v2 divided by v2 v2. Third component or third coordinate of z in basis C will be z dot product v3 divided by dot product v3 v3. So we just go and do the work. So dot product zv1 is -4. Dot product v1 we already computed, it was 8. zv2 we compute, we get -5. v2 is 11. And zv3 you get 8 over 11. And v3 we get 8 over 11. So now all we need to do is just plug the numbers in. So the first one divided by the second, so -4 divided by 8. So you can simplify this a little bit. -1 over 2 if you wish. And then the second one is -5 over 11. And the last one is 8 over 11 divided by 8 over 11. So that's 1. Obviously, if we make any errors, we need to correct it. So that's how you get the coordinates of a vector in orthogonal basis. Very simple process. If we want to get the coordinates of z in orthonormal basis, D, so we have vectors W1, W2, W3, those are unit vectors. We just made them, so we know they are unit vectors. So we use actually the same formula, so z dot product W1 divided by W1 dot W1, but W1 dot W1 is 1, so we don't write it. So you see the beauty when you have orthonormal basis, the coordinates are very simple. So we do the computation here. If we don't make any errors, this is what we get for each one of them. Obviously we can simplify a little bit. We don't have to, but it would be cute. Obviously, the last step with simplification, you can make some errors, so be careful. So what we see here is vector z has different coordinates in different bases. Obviously, in basis b, to get the coordinates, we had to solve a linear system. But when we deal with bases c and d, those are orthogonal bases, then we don't need to solve a system to get coordinates. We just need to use the formulas. So that simplifies our work a little bit. So now we are going to see what happens if we have vector in R4. Obviously it's going to be longer and a little bit more complicated. Here is an example in R4. So again, Gram-Schmidt procedure is here. What I would like you to remember is that the vectors obtained from Gram-Schmidt procedure are orthogonal, and also all scalar multiples a v1, b v2, c v3, d v4 are also orthogonal. So if I multiply v1 by some number, it will still be orthogonal to the other guys. Okay, so that's obvious from the dot product. So if v1 and v2 are orthogonal, any scalar multiple of v1 and v2 will be also orthogonal. That's not a problem. And I will use it here. So this is to give you a trick that you could use if you wish. If you don't want, it's fine. So here I have a basis b of R4. You can check it by computing determinant. It's different from 0. Or getting an echelon form and observing that you have 4 leading entries, and then you'll have that all your 4 vectors are then independent. Okay, so I have a basis B, and I want to use Gram-Schmidt procedure to get an orthogonal basis called basis C for R4. Well, again, V1 is U1, we start with that. And here I'm doing something a little bit different. I'm actually applying the second step, but you'll see what I'm doing here. You saw that in these procedures we have a lot of fractions. Eventually, at some point, if we normalize things, we have square roots. So that's not that nice. It's a little bit ugly to work with. So look what I'm doing here. So for V2, with a little head, like a Chinese house. So U2 again, is the V2 head is U2 minus U2 projected on V1. So I just copy U2. So the dot product U2 V1 is 2. Dot product V1 V1, you compute, you get 4. And then V1 is here. So I do the algebra and I get this. So I have 1 over 2 times this vector. Obviously you could have 3 over 2, 3 over 2, 1 over 2, 1 over 2. So you'll have a fraction in each single component. So that's not so nice. And now I'm going to use this property here that any scalar multiple of orthogonal vectors will also be orthogonal to the guys. So this vector v2 hat is orthogonal to v1. You can double check if you wish. But also if you multiply this vector by 7 or 2 or 11, the resulting vector will also be orthogonal to v1. That's what we know from the properties. So instead of me having to deal with fractions later on in the process, well, I'll multiply this vector by 2 and get rid of the fraction. I'll get this guy. So this guy is my v2 because I prefer vectors without fractions. So this is still orthogonal to v1. You can just do the dot product. So v1 is 1 minus 1 minus 1, 1. So 3 minus 3 is 0, 1, negative 1 plus 1, 0. So you see dot product will be 0. That's fine. So the idea here is I will conveniently multiply by a constant to get rid of the fraction. So then I have a nice vector here for v2 because I now need to use it later on. And then I need to do the dot products, and I don't want to deal with fractions. It just complicates my life. You could, it's fine, you could just apply blindly this and deal with fractions, it's all okay. I'm just showing you a way to avoid fractions as much as possible, because this vector is orthogonal to V1 just as its scalar multiple is orthogonal to V1. So that's why the properties are important. We can get smart with the properties. So now V3, again I'm putting a hat here because I don't know, probably I'm going to get some fractions. So I use my Gram-Schmidt procedure for V3 as usual. So U3 minus projection of U3 on V1 minus projection of U3 on V2. So I need to compute all these dot products. So I copy U3, dot product U3 V1, you can compute it, it gives you 1. V1, we already computed it is 4. Dot product U3 V2, you compute it gives you 15. And U2 gives you 20. And you copy U2. You see here, this dot product became easier to compute than if I had a fraction. And then I would need to combine that fraction with V2 that would have a fraction is just a mess. Too many fractions. So I'm trying to simplify things. Okay, so now I still have some fractions. I can do some simplification here. So I have 15 over 20. So that's 3 over 4. So I divide by 5. So I get 3 over 4 here. So I have this to compute. Okay, so after suffering a little bit, I get something like this. You can compute and see that I haven't made any errors. So I can factor 1 over 2, so I get this vector here. Again, I have a fraction. You can keep going with it, it's fine, but I don't like fractions. So I know that any scalar multiple, obviously we want a non-zero vector, so any non-zero multiple of this vector here is also orthogonal to everybody else. So I'll just multiply by 2 and I get this guy. So I'm basically taking the vector without the fraction. Okay? So that's my V3, because I need to keep working with V3 now to get V4, and I don't like fractions. If you wish to work with fractions, it's fine, but it's going to be a hell. So V4 with a hat, just in case I get some fractions. So again, I use the formula. So I get all these pieces here. Hopefully there's no error. And then I see the only common factor here is 60. So I'll try to bring everything out of 60. So this guy is 60 over 60. So that's why we have 60 here. And then, so basically what I'm doing is just making sure that I have common denominator 60 and then doing all the computations. I get this. So here, at this point, I did one extra step. I realized that I could divide by 4. But I don't have to. Okay, I could just stop here and take this vector immediately. Boop. And that would be my V4. But okay, I did one extra step and then said, oh, I still have a fraction. I couldn't see it before, apparently. And then I said, okay, let me just multiply the guy by a number different from 0. And I'll get a vector that is perfectly legitimate vector, V4. And this guy is also orthogonal to V1, V2, V3. So that's how I get the basis C, V1, V2, V3, V4. That is an orthogonal basis for R4. Again, this is just to show you that you can avoid fractions a little bit and simplify your life. Whenever you have, at the end of your process, something with fractions, you just take the guy without the fraction. Make sure you do the algebra properly. And this is because we know that if U and V are orthogonal, then 5 times U dot product 7 times V is also orthogonal. So that's simple property. So this is my orthogonal basis obtained by Gram-Schmidt. Obviously, we could push it one step further and get orthonormal basis by normalizing every single one of these vectors. So that means I will need to compute norm for V1, V2, V3, V4, and then divide each guy by its norm. I'm not going to do that. and that would be my orthonormal in that case with W's, but I'm not doing it here. So all I wanted is to show you that you can use a property and simplify your life a little bit when it comes to Gram-Schmidt process when you have all these ugly fractions. So that's about it. So that's all we need is pretty much to know how to apply Gram-Schmidt process to transform some basis B into an orthogonal basis. And if we are asked, we can transform it into orthonormal. Once we get orthogonal, we just normalize each vector and we are done. And second benefit of orthogonal basis is that it's easy to find coordinates of a vector in an orthogonal basis. We saw that previously. We just need to do ratios of dot products pretty much. So that's quite easy to do. It's much easier than solving a linear system Ax equals b. So that's about the chapter 6 and everything you need to know, how to apply Gram-Schmidt and how to find coefficients or coordinates of a vector in an orthogonal basis or an orthonormal basis. So those are only two things that you need to focus on: Gram-Schmidt process and finding coefficients or the coordinates of a vector in an orthogonal basis. Here are again some practice problems for you in yellow book and white book. I suggest you solve them, and one extra problem with the basis for R4, and you need to transform this basis into another basis that would be orthogonal, and then transform that one through into orthonormal basis. So this is just practicing Gram-Schmidt pretty much. So I hope it's going to be fine. This is easy material normally, and it shouldn't be a problem. A couple of practice exercises should be enough.